It's my pleasure to introduce our visionary speaker for this morning. Antun Domic serves as the Executive VP and General Manager of the Design Group at Synopsys, where he is responsible for leading the development of the company's implementation and analog mixed signal product lines. I just had the opportunity to chat a little bit with Antun about our history together. We worked on the last VAX and on the first alpha, and he continued to work on the second alpha. So before Synopsys, he worked at Cadence, and before that, he worked at Digital Equipment Corporation in Hudson, Mass., and before that, he worked at MIT Lincoln Lab in Lexington, Mass. Dr. Domic holds a BS from the University of Chile and a PhD in mathematics from MIT. Please welcome Antun to the stage.
Well, thank you, Soha, for that nice introduction and the opportunity to give you some thoughts of what we see a little bit in the semiconductor industry and how that affects the design automation area. Particularly, I'm going to talk about the tool area, that's where I have worked for so many years. So today we're facing an interesting situation. If you look at the number of 14 nanometer transistors that fit on a 300 millimeter wafer, they count that this is more stars than on the Milky Way, and that's a truly amazing number. I have always been startled when the million transistor barrier was broken, and now we're breaking 10 billion, so certainly we're way ahead. But at the same time, things do get smaller. When you see those little dots in the background are actually atom pairs. The whole area is about 7 by 4 nanometers. And this tells you that we're getting to the infinitely small, where now we are literally counting transistors and what will happen as shrinking continues. So let's take a look at what we see in this infinite world of opportunities as we confront the infinitely large and the infinitely small. If you look at the emerging technology nodes, particularly what happened when non-planar CMOS appeared, the so-called Tri-Gate or FinFET introduced by Intel commercially in 2011, now the industry has quickly moved to FinFETs at 14, 16 nanometers. The double patterning techniques had to be used here to deal with routing problems, and we're looking at multi-patterning ahead for 10. So if you look at this type of technology, obviously there are a tremendous amount of effort to bring them up, and there is a cost in designing chips at this. So we see the applications of this as being less. Obviously, CPUs, large graphic chips, FPGAs, and obviously the very high volume wireless chips. At the same time, we see the established technology nodes playing an increasingly important role. If you look, we have a track now of automotive. 90 nanometers is a prevalent technology in automotive applications. You see 40 and particularly 28 nanometers having a long life ahead. You may have heard of a recent agreement between Samsung and ST, for example, to provide a fully depleted SOI technology at 28. TSMC introducing new families at 28. People are expecting wide use of this going forward. If you look at the other aspects that you can consider, analog mixed signal, true 1.5D and 3D ICs, MEMS, that will guarantee you an even longer lifespan for these technologies. And obviously, particularly for analog IP, this certainly will extend the life of it. I will not talk much about IP, as the next speaker will give you much better insights than I could on this. But let's take a look at what happens with a car. Obviously, this is a car that is not going to be introduced in the distant future. I was told there was one at the Munich airport few weeks ago. So we're seeing here that the car will be incredibly smart, have very advanced electronics, but the electronics at 14 nanometers are going to be on the phone of the car driver, not in the car. So looking ahead then, to just pick one area, that is automotive, you are going to see that the content of the value of the electronics is going to reach maybe 50% of the cost of the car. Other applications like medical equipment and things of that type will become increasingly important, and obviously their reliability and other considerations are going to make them use a lot of these established technology nodes. So let's take a look at what is happening there, and we always seem to take a little bit for granted the older technology nodes. So let's look at what makes some of these chips interesting, and let's pick one, a very 180 nanometers. One could say, well, what's the big deal? This is a controller for power that goes into tablets and portables, but it has 12 voltage islands. This is a recent chip. I don't think this chip would have been able to be designed at that level of complexity with the tools that we had when 180 nanometers was the latest technology. You look at another case, a lot of combinations of technologies on the chip. If you look at these chips, they have bipolars, they have DMOS. There is a digital part that is the traditional part that we tend to look in synthesis and place and route, and those are the small red squares on the chip. So a lot of activity here. And if you look at this diagram, I will not go through all of them. When leakage became a serious problem, the EDA industry took a lot of effort in doing power management techniques. And if you look at multi-voltage, clock gating, all the multi-threshold optimizations and so on, this just gives you a little bit of all the techniques that are being used. And I think this is what is enabling this extremely advanced chip at the established technology nodes. Let's look at another area. This may not look too interesting. If you look at the hashing on the different polygons, you will see that there is something a little bit more interesting. And if you color them now, you will begin to notice what are we trying to do here. These are experimental work that we're doing with a number of foundries with respect to multi-patterning. There you see 3 colors being used for routing. And the effort that the EDA industry put for dealing with the double patterning problem brought huge advances in routing. And let me show you some of the consequences of this. If you look at this 28 nanometer chip, you don't see very much the left one side, unfortunately, but that's a part that using the best techniques of synthesis exploration and floor planning, optimization of logic synthesis combined with placement and place and route, you can do a very complex 28 nanometer chip with higher utilizations going forward. So that's where we see the advance in some sense. But if you look here, this is a chip in the 160 nanometer area mixed signal, where initially it could not be routed using more traditional place and route and logic synthesis, but taking this pre-placement into synthesis managed to be able to do this going forward. And second, for example, if you add other pieces of reducing cost by reducing layers, reliability requirements of double vias and high utilization, this has been made possible really for the advances that were driven by the double patterning techniques that needed to be put in routing. So going in that direction, you continue, and this is something that may look like a board, but it's not a board. This is an interposer routing being done on a digital place and route tool. And this is what is enabling today the fact that the MEMS, for example, and these stackings are really possible in these systems on a package. So to give you a little bit of a summary here, I believe that the established technology nodes are going to be driving needs of advanced EDA tools. These new technologies, many of them initially targeted to the advanced nodes, are going to play a critical role on the established nodes. I believe also that it is not possible for the EDA industry, given the financial constraints that we have, to develop parallel set of tools. In the past, the established nodes were a little bit neglected, good enough, and so on. I believe that these new applications, good enough, will not be good and will not be enough. So the EDA industry will have to provide a set of tools that should be able to help people to differentiate by design. Differentiating by semiconductor technology, as you can see, will be very difficult. The sources of semiconductor technology are becoming less and less, and the life of the established nodes will be longer. So design is going to be critical, and from that perspective, that should foster innovation in EDA and the ability to have sets of tools that can span from the most advanced nodes to the established nodes. To close, not only we will be enabling the semiconductor industry and a lot of new applications, but also we're enabling new capabilities in people. It's very interesting to see the Google car that obviously contains an incredible amount of electronics, but also what these things are enabling for people. This is a YouTube video that essentially has a driver that is practically 100% visually impaired. So thank you very much, and that concludes my talk.